So thank you for the introduction, and thank you also for this invitation. So yes, we are going to talk about geomorphology and surface processes, and I will try to take you to a journey between data and models with a two-way ticket, trying to understand how numerical models can help us understanding our data, and also trying to see how we can better constrain the models with inputs and outputs from the data from the observations. So this is the result of a long-lasting collaboration between GEOAZUR at the University Côte d'Azur in Nice and the CEREGE, and also with other people, many people from different labs in France, especially in Grenoble and in Nancy, and also outside France. So yes, I'm going to show you mostly examples of a very regional study, which takes place not so far from here. So Aix-en-Provence is close to the lower left corner of this map. So this is a topographic map of the southern French Alps and Provence, where you can see the high altitude, around 3,000 meters area of the Mercantour Massif, which is surrounded by the subalpine fold and thrust belt here, and the Provence foreland, which is here. And of course, this region here is facing the Mediterranean Sea. And if you look at the topographic gradient, you can see that we go from 3,000 meters in altitude here to minus 2,200 meters in the deep basin. So we have a large topographic gradient here because the distance is something like 50 kilometers. Of course, the gradient is much smoother in this direction. So if you look at the geology, a very short introduction about the geology, because it will be important for the rest of the talk. We have mainly crystalline rocks here in the Mercantour Massif and in the Mort Massif. So the Mercantour Massif is the old Variscan basement of the European crust, which has been uplifted by the alpine orogeny. And it's surrounded by this fold and thrust belt, which is dominated by sediments. You have Mesozoic and Cenozoic sediments, which are mainly carbonates, but with also some quartz-bearing sediments. You have sandstones here, which belong to the previous foredeep that is related to the early stages of the collision. So now back to geomorphology. And if we look at some characteristic landscapes of this area, we will, of course, observe very different landscapes. If we go in the upper part of the massif, as you can see here on this picture, we see typical landscape of the higher mountain with the crest here and some remnants of glacial landforms, with here some glacial and fluvio-glacial deposits like moraines and so on that are being incised very recently by these rivers. But if we go downstream, closer to the coast, of course, everyone is familiar with that, we see very different landscapes. These are two examples here in the Vesubie and Estérons rivers. All these rivers belong to the Var river catchment. And as you can see, very different things with evidences of vertical down-cutting of the bedrock by the river. So here it's purely fluvial morphologies, and you have a very nicely preserved vertical cliffs. Here, it's in both cases, it's in upper Jurassic limestones, and so different processes, different landscapes, but all these landscapes have a common history because they are in the same catchment, they are in the same area, so they have a common history, both in a climatic sense and also in a tectonic sense. So, speaking about the influence of glacial history on this landscape, what do we know? So this is a map that has been constructed by a former PhD student, Thibaut based on existing literature, to synthesize the possible extent of the glaciers during the last glacial maximum in the Mercantour Massif. And what we can see is that these three main rivers, so the Var River, which is the main stream, and its two main tributaries, which are the Tinée and the Vésubie rivers, have been covered by glaciers in their upper part. And if you look at the Tinée River, it's more than its half of its length that has been covered by glaciers. So this is what we know, but what we don't know is what was the effect of this glaciation and on the deglaciation on the dynamics of incision in the river system. So if we look now at another control on river, on the landscape evolution and behavior, it's the tectonics. By tectonics, I mean not only plate tectonics, but any kind of horizontal or vertical motion that can occur. And if we look at what happens now in this area, well, it's not so clear. Of course, we have seismicity, as you can see here, so our study area is just here. There is seismicity, but it's diffuse seismicity. It's low to moderate magnitude earthquakes. There seems to be some consistent reverse faulting earthquake mechanisms, but there are very few identified reverse faults, except with the exception of some faults which are here at the bottom of the margin at sea. And if you look at GNSS velocities, it's even less clear. So these are GNSS velocities in an Eurasia fixed reference frame, and as you can see here, nothing seems to stand out of the noise. There is no clear shortening between, for instance, Corsica and the continent in this area. So where do these thrust mechanisms come from? Not so clear. And when it comes to vertical velocity, there is maybe something that's a bit clearer, a signal that seems a bit clearer, but with some uplift, very nice uplift signal in the Alps, but which seems to vanish when we reach the southernmost tip of the Alpine chain. Some subsidence may be along the coast, but it's not always very clear, and it's very low velocities. It's less than 1 millimeter per year, especially if you compare with a strong uplift in the rest of the Alps or strong subsidence in the Po Basin, for instance. So based on this, we can ask many questions, and what I was interested in is to understand the timing of the glaciation in this area, and how it has impacted the dynamics of the landscape, and especially river incision. And in turn, we wanted to better understand also what is the link between climate. By climate, I'm not speaking about real climate model like we have seen it during these days, but between the runoff in the rivers, the amount of glacial meltwaters in the system, the amount of erosion it creates, and the tectonics. And by tectonics, again, it's more like isostatic motions than real far-field plate tectonics. So what can we do? What is interesting is that rivers respond to all these processes. They are sensitive to climate variations because climate will modulate the amount of precipitation. It will modulate the amount of water that is stored in the high altitude areas during glaciation, and it will also modulate the sea level. But tectonics, vertical motions, will also change the slope of the river channels, and so it will also change the rate of incision. So rivers are good candidates for trying to understand all these interactions. So how to do that? To do that, we must quantify river incision rates, which means we have to measure a time and to measure a distance. Time will be given by the, this is where CEREGE comes into play, because time will be given by the age of exposure of the rocks that have been inside by the river to the surface, and age is simply what you measure on the cliff. So we have several sampling points here, many points in the Var catchment here, some points here in other catchments east of it, and we have 2 points here, which I'm not going to talk about a lot, which are in the Durance river system. So what is a sampling strategy? So it's both simple and complicated. you have to find someone who is okay with that. This is Yann Roland, who is a geologist, geomorphologist, and a climber. So very, very good. So basically, you have to find a spot where you have a very nicely preserved river inside cliff, and you have to take samples and measure the topographic shielding, and measure also the distance between the sample and the riverbed. So yeah, it's just data, but it's not so easy to get this data. And you also have to avoid places where the cliff has been degraded, for instance, by rockfalls, which occurs sometimes. So all these samples have been collected, and they have been processed, and the ages, the exposure ages have been computed here at the CEREGE, and of course we had many discussions between our teams. So this is an example of a compilation of the ages we had here in the eastern part of this domain, and I'm going to try to explain what we can get from the simple analysis of this data, and then later on what we can do with models. So as you can see here, so on the left figure, on the x-axis you have the exposure ages in thousands of years, and on the y-axis you have the altitude of the sample above the riverbed, so that the slope, if you can draw a slope like it's possible, for instance, here, it's just the incision rate, the river incision rate. So yeah, you see we have many different tendencies. So first first question you can ask is there, for instance, a north-south gradient between the high altitude points and the low altitude points? So it's both a north-south gradient, it's also an altitudinal gradient, of course. Well, of course, you can see that these rainbow colors seem to be reflected in this graph, but in fact, it's not really a gradient. We see rather three different groups. There seems to be a first group here in the upper part of the Tiny River, which seems to show, as you can see here, very recent incision, younger than 10,000 years, and at a rate which is extremely fast, around 1 centimeter per year, which is much, much higher than tectonics or whatever. At the opposite, close to the coast here in the Paillon River, we have very old incision, starting by old, I mean several tens of thousands of years. It's older than 80,000 years. Points are very scattered, but we can draw a line along an incision rate which is less than 1 millimeter per year, 0.2, and which is closer to the uplift rates that we can assume from GNSS data. And in between, we have this group of four samples that seem to show maybe more complicated behavior, with something that begins around 30 to 20,000 years, which is very scattered in the first period here. As you can see, there are yellow, green, and blue dots everywhere, and which seem to align along a maybe clearer trend after 10,000 years along an incision rate of 1 millimeter per year. So very different behavior between all these river systems in the same catchment, with the exception of the Paillon River, which is in a different catchment. So another question is there an east-west gradient? Why not? But there is not. And as you can see, if we include this time this point in the Verdon system, and if we look at this rainbow here in the data, we can't see it anymore. So we find this consistent value around 1 millimeter per year, after 10,000 years. And we find also that these 2 points, the yellow and the purple one, align around an incision rate of 0.2 millimeters per year. Okay, so what does it mean? So to understand what it means, just looking again at the data, we can examine a little bit further the central group here, and try to see what are these different behaviors that we can observe before 10,000 years. So this is the work also by Thibaut Cardinal. So he has examined into more details every different sampling points. And what he has seen is that, for instance, in the Vesubie River, which is the river, in the Vesubie and Tinée River, which are the rivers that were directly covered by glaciers during the LGM, we have a first stage of fast incision around 3 millimeters per year after the LGM up to 9 to 10,000 years, and which slows down to 1 millimeter per year after. Whereas, if we look at the rivers which were not directly connected to glaciers, meaning that along their stream there was no glacier, but they were connected, there were tributaries to a main river which was covered by glaciers, so that is what is implicitly indirectly connected. It's the opposite. We have a first period of low incision rates, 0.5 millimeters per year, and then it increases to 1 millimeter per year, around 10 to 12,000 years. So different behaviors depending on whether the river is directly connected or indirectly connected to the glaciers during the LGM. So this was a possible interpretation of this behavior, is to interpret this as the direct influence of glacial meltwaters into the river system during the deglaciation, which will impact the amount of runoff in the main stem, but not in the tributaries, and which will increase the incision rate directly after the LGM in the main river. And during that time, nothing happens really in the tributary. So the tributary will be aware that there is a problem just once the main stem has started to incise in the bedrock, and at this time there will be an nick point that will propagate in the tributary, and in the tributary, so you will see is the first period of slow incision that is followed by a period of fast incision. So if we look at, if we compare this with previous estimates of the timing of deglaciation, and also this is a compilation based on different data, we see that indeed we have a consistent timing of deglaciation around 17 to 20,000 years in the main part of the Tinée River, and the only exception is the very, very, very high altitude remnants that have been free of ice only after 11,000 years. So how can we very simply interpret this data? So we can maybe interpret the very slow uplift rates, incision rates, sorry, as related to a steady state between river incision and uplift. So maybe this very slow incision rate reflect the uplift rate of this area. And oppositely, we can interpret the very, very fast incision rate as the incision of landform, relict landforms and deposits in very high altitude areas. And in between, this group in between reflects, in fact, the effect of the delayed effect of the deglaciation, which is different between the main rivers that have been connected to glaciers and their tributaries. So a first step of conclusions are the rivers incising at pace with a tectonic uplift. The answer is no, except maybe two of them. They incise much faster than what we can measure as a tectonic uplift. So we are, in fact, in disequilibrium landscape, which means that there is a topography that still has to be eroded, and it's eroding, at least as far as river incision is concerned, very fast at rates equal or above 1 millimeter per year. We have also shown that there is a complex response to glaciation and deglaciation cycles. In fact, we can see only the last cycle. We cannot go back in time further than that. And what have not been, I won't talk about, but which is also important, is there is a dependency on lithology. And the propagation of nick points is also dependent on the lithology that they will cross along their journey from the outlet up to the headwaters. So what we have to understand now is that, in fact, these are only local measurements. Means you take a point along the river channel, and you go sampling it, and you have an incision rate. But the thing is that the river incision rate varies a lot from the headwater down to the outlet of the river, because it depends on many things. It depends on the slope, it depends on the drainage area, it depends on the channel width. So there are many factors that will control the rate of incision of a river, and if you have only 1 or 2 measurement points, well, it's difficult to assess many things about the complex behavior of the whole catchment. So what can we do now? Now, in order to better understand this data, we need to have models. And these models, although they are necessary simplification of what happens in nature, they are necessary to understand the catchment scale processes. So a first generation of model, maybe not a first generation, but it's some models that have been, they are still very widely used, are based on the analysis of river longitudinal profiles. So this curve here is simply the altitude of a river channel along its path, okay? And it's very interesting because if we assume the very, very well-known stream power law in the field of geomorphology at least, we can draw a relationship between the incision rate here, the drainage area, which is easy to measure, and the channel slope, which is also easy to measure, at least on DEMs. And if we make the assumption that at least on a part of the channel, we are at steady state, meaning that the incision rate is equal to the uplift rate, then we can easily draw a relationship between the river slope, the channel slope, and the uplift rate, provided we know something about this coefficient K, which is the erodibility coefficient. So this method has been used a lot because it's not so difficult to use. It provides really interesting information on not the whole catchment, but the whole length of the river, of the many different rivers that you can observe. Of course, we have GEM, and we have to estimate this value, which is not so easy. But as you can see here from this study in Africa by Gareth Roberts and Nikki White, they used these channels to invert from time variations of the uplift rate of a given area that was a priori constrained. So you have to know where the area is uplifting. And you have here inverted uplift rate through time, and they have shown that you have 2 peaks of tectonic uplift in this area. So this is very interesting, and but we have 2 unknowns, in fact. We have the erosion coefficient K, which can vary with time, and we have the uplift rate, which can also vary with time. So it's 1 too many. But what we can evidence, this is a study by Liran Goren, is that provided you know, you have some knowledge about the uplift history, then you can recover the variation of the erodibility coefficient, which is here a proxy for climate. And also, the other way around, if you have some knowledge about the variation of the erodibility coefficient, then you can reconstruct by inversion of the river channel the variations of the uplift rates. So it's a rather powerful method to constrain these climatic and tectonic histories. So this is going back to the Mercantour and Southern Alps massif. This is what we have done with Liran especially, in this upper part of the Tiney River. And as you can see here, there are many tributaries to the Tiney River on its left bank. And there are very similar channels. They have the same length and they have the same profile. So there are many of them. Some of them were discarded because there were too many glacial imprints. And our reasoning was as follows. If we can measure and invert the uplift rate of all these tributaries, in fact, what will it give? It will give the incision rate of the main stem. It's exactly the same thing as if you had a normal fault here, and if you are trying to measure the uplift rate of the footwall. Here, it's not a fault, it's a river which is incising its bedrock, and you're trying to measure the effect of this incision in the tributaries that will respond to this base level drop. So this is what we did, and in fact, here in this figure, what you see is the different uplift rate history. This has been normalized between 0 and 1 of all these tributaries. And on the x-axis, what you have is time. So the present is to the right and the past is to the left. And what is interesting is that these histories bear similar characteristics. Of course, all these curves are not exactly the same, but as you can see, they show a peak of fast incision in the recent period. In the recent period, I mean after the LGM. Then it decreases, and there is also a peak of fast incision in the other warm period that follow MIS5. So there seems to be consistent, although with some variability, pulses in incision rate in the teenage channel that seems to respond to climatic changes. So this is one of the other conclusions. We evidenced what we think is a response of the main channel to climatic variations with faster incision during interglacial periods. And what we could see also, that we could image waves of fast incision traveling into the river channel. You have 3 snapshots here in the Tine River. And these waves can be also correlated with the onset of some landslides, like the Lac La Plera landslide, very famous landslide, which is occurring here. So, okay, so a next step towards modeling the evolution of the relief. Still, it's something that is very simple. We do not take into account the possibility that the drainage area changes with time, which is false. It has changed. We do not take into account the effect of hillside processes. Here, we only consider what happens along the channel in the river, and the rest of the landscape is not taken into account. And finally, we have only few constraints on the time scale. Here, the time scale of evolution that you find here, that is correlated to the global temperature, is only constrained with the assumption that you have on the erosion coefficient. So we need to go a little bit further. So, in fact, how can we go further in this understanding at the catchment scale, at the regional scale, on the dynamics of this topography, of these catchments? In fact, we have a lot of data. We never have enough data, but at some points we can be satisfied because we have some of them. So we have high-resolution digital elevation models. We have some dating on the river incision. And we have also, this is work by Apolline Mariotti, we have also quantitative data on denudation rate. So she has done a lot of sampling in the Var catchment to estimate present denudation rate in the river sounds here, as you can see here. And she has also worked on submarine cores in which she used the beryllium-10 signal to infer denudation rate on land. Okay, so the question is, do we need more data? Certainly, but the question is also how to process already the existing data, how to mix everything together and to find a way to explain all this data together. So what do we need? What are the basic ingredients we need? We need something that describes landscape evolution, at least with maybe the minimum necessary to understand all this. So we need erosion, transport, and sedimentation laws on land and also at sea, because the submarine cores have been taken in the deep basin. We need to include sea level variations. We need to take into account the fact that the Mercantour Massif was covered by ice from time to time. And we need also to take into account the fact that sea level erosion and ice cover will cause an isostatic response of the lithosphere, so some uplift and subsidence. And maybe other things that are not present in the model, but maybe that we should take also into account. And we need to make sure that the result is consistent with the observation. What do we have? We have river profiles, we have river incision rates, and we have the beryllium-10 signature in sediments. So what we did is try to incorporate all this in a forward model of surface evolution in the Badland codes, which has been developed by Tristan Salle, simply by implementing the possibility to trace a beryllium-10 production, erosion, and sedimentation in this model. So how does it work? So the ingredient of the forward model are just the stream power law, which describes river incision, diffusion law, which describes hill slope processes, so rock falls, hill slope creep, and so on. Everything is described by a diffusion law. And some also conditions that will control deposition of the sediments on land or at sea. So it can be deposited if the slope is lower than a given threshold. They can be deposited around the base level in a delta or in closed depressions, for instance. And then you can also compute, we had to compute beryllium-10 production on land in quartz-bearing rocks, given the geological map that we have. And we also have to compute the mass balance in order to estimate the beryllium-10 concentration and quartz concentration in the sediments that are being produced and exported down to the deep basin. And finally, we can add also flexural isostasis with an elastic plate model in order to compensate for the mass distribution due to ice and erosion. So, okay. So this is basically what we did, and as an example, you have here the ice cover, maximum ice cover of the model in the Mercantour Massif, which is modulated by the sea surface temperature with the thaw rate that is given from the literature. And you have also the sea level changes, which will change the amount of erosion that you will have close to the shoreline. Okay, and in addition to this, sorry, I'm going back just one slide. In addition to this, so we needed to implement sediment transport down to the deep basin. Opposite to many river systems, there is almost no delta at the mouth of the Var River, as you can see here. And so there is very little sediment deposition at the mouth of the Var River, and most of the sediments are exported down to the deep basin here. There is a sedimentary ridge here, which is the Var Ridge. And so there is a lot of export of the continental sediments down to the deep basin. So we had to find a way to implement this in order to compare the signature of the deep marine sediments with what happens on land. So this is done very simply by assuming that you can have submarine hyperpycnal flow when the sediment and water flow that comes to the base level reaches a certain density. So this can be achieved either by simple mass balance. You compute the amount of water you have, you compute the amount of sediment you have, and you see what is the mass of the flow. Or you can use rating parameters also that are applied to the Var River, that are very specific to the Var River, and which will give you approximately the same thing. And this is how you can trigger submarine high-density flow down to the deep basin. And then you can also use some criteria to determine when and where these sediments will be deposited. So this is the main implementation we had to do in the model. So now that we have this, then we can try to understand how landscape erosion will be reflected in the beryllium-10 signal that we can observe on land in river sediments and at sea, which is important because we can understand what is the part of the signal that is relevant to the climatic processes. So what we can do, for instance, if you have an altitudinal profile like this, so this is the on-land part. Between the time t and delta t, you have some erosion here, and you can compute the beryllium-10 concentration in these sediments at every time. And you can compare it, and from this beryllium-10 concentration, you can compute an apparent denudation rate at this time. And you can compare it with the true denudation that is given by the model, so that you can see if your signal does reflect what really happens in the model. And you can do the same offshore. So you can take a slice of sediments, see what is their age, what is their barium-10 concentration, and does it reflect the same denudation? If it's the same for the same time period, what it means is that there is some instantaneous transfer of sediments that are produced on land to the deep basin. So you have the same signature, the same response, same record. But if it's different, if for a given delta T you have a different signature here than what you find in the sink here, it means that something is happening here, that you have some storage and some reworking of the sediments and so on. So this is how maybe we can try to put all this data together. So this is an example of a test that has been done. And in this test, we have produced during 100,000 years 2 periods of very fast, very high precipitation that will that will produce high incision, and we have compared the true denudation rate that is given by the model, which are the blue dots here, with the one that is given by in situ sediments, which are the sediments that are produced here near the massif. So as you can see in the red curve, it's almost the same signal. It's a bit different because there are not quartzic rock everywhere, so the beryllium-10 signal oversamples some areas, and some areas are also eroded but are not sampled by this signal. So there is a little discrepancy, but it's normal. But if you look at what you find in submarine sediments, so there is a synthetic core that has been sampled here, it's quite different. In fact, the background value is a bit less than what is produced in situ and measured in situ. But most of all, you don't see anything corresponding to these 2 periods of very fast erosion. So some discrepancies on land, which are completely normal and can be corrected for, no problem. And in marine sediments, we cannot see anything really relevant to what happens really in the model. Another way to understand this also, to better quantify maybe what happens during the sediment production and the sediment deposition, is to make some artificial dyeing of the sediments. To do that, we simply impose a very high beryllium-10 concentration here in the massif. Is completely artificial. It's exactly like if I were dyeing the sediments with a bright pink and see what is the color of the sediment that have been deposited later on in the deep basin. So there is an area here of artificial beryllium-10 enrichment during 5,000 years, and we are just sampling here at sea what's happening. And as you can see here, there is a signal that occurs, so it's the blue curve in the deep basin, that seems to begin during the period of beryllium-10 enrichment on land in the high massif. But in fact, if you look at the time it takes to reach its maximum, it's already more than 10,000 years later. And if you look at the time it takes to go back to the normal, which is 0, in this case, it takes more than 50,000 years. So what it means is that, in fact, you can see pulses of beryllium-10 enrichment in the sediments, but the signal is spread over a longer time period than what occurs at the source. So it will be very complicated to disentangle what you see in the marine sediments because of this. So based on this, the challenge was to find a model that could explain everything. So I'm not going too much into detail to show you all the models that we have done, but one of the best fitting models is the one that shows an increase in precipitation rate from 0.5 to 0.7 meters since the last 20,000 years, which incorporates isostatic rebound, the presence of ice, and the presence of, and of course, sea level changes. And with this model, we were able to predict, except for one river, which is here, incision rates that are consistent with observation. And we were able to predict here a beryllium-10 concentration, average beryllium-10 concentration, this is why you have vertical bars here, in the deep basin that is more or less consistent with measurements. As you can see, there are some points that stand out outside this, out of this curve. So how much time do I have? 2 minutes? Okay, so I will skip. So short conclusion, we have a lot of data, but they are sometimes very local, and they show different behavior and different things. We have complex models, but these complex models, once we have found the best fitting model, we are never sure that it is really the best fitting model. Now, to go further, we need to know what is the best solution to this complex process. And this is my new research topic, is to not only run forward models, but also to run inverse models. So there are many families of inverse models. The aim is always to minimize the misfit between outputs, topography, denudation, whatever, and observation. And to use this misfit to change model parameters and to find the best fitting model parameters, which are erosion coefficients, initial topography, or uplift rate, whatsoever. So there are many methods. I'm going to go a bit faster on this. There are many methods that can be used to inverse landscape evolution parameters. But most of them rely on a very large sampling of the parameter space. And the more complex is the model, the larger is the parameter space, and the more complex it becomes to sample it. So we have many ways to sample it in a very efficient way, but still, if you multiply the number of parameters, it becomes impossible. So these are examples of what I've done in inversion procedure. But an interesting method is what we call a gradient method, and it's the adjoint method. So in a nutshell, the adjoint method is, in fact, once you have defined an equation that describes your forward model with a variable of interest, here is the altitude, you can define also an adjoint equation, which is applied to an adjoint variable. And the interest is that this adjoint variable incorporates both the constraints that you have on your equation, because you need to fulfill this constraint, and also it incorporates the information on the variation of your misfit function with respect to your model parameters. So this way, you have to run the forward model only once, and then if your initial guess is not so far from the solution, then you have a gradient of the misfit function that you have to follow in order to minimize it. So it can be used, of course, for optimization, means for minimizing this function and finding the best parameters that you're looking for. And also it can be used for sensitivity analysis, meaning to see which part of the landscape, for instance, are most sensitive to parameter variations. So I'm going to skip all this just to show you some sensitivity maps that we have done in the French Massif Central, which is here. And based on this method, we have shown that there is a larger sensitivity to the fluvial erosion coefficient, as you can see here, along the southeastern escarpment of the Massif Central, than to the diffusion coefficient. And with this method, we can also invert for spatial variability of the erosion parameters. Here there is an example of an inversion of the fluvial erosion coefficient in the same area, and you can see that this is a true model and this is the inversion. So in places where the landscape is sensitive to variations of this coefficient, then we can retrieve the actual value that was imposed a priori in the formal model. So can do the same also for the initial topography. This is an example of a reconstruction of the initial topography of the model, and also to uplift rate, but I'm going to skip that to reach my conclusion. So we have more and more quantitative data, which is very interesting, and we have also more and more complex processes in the landscape evolution models, which renders difficult to sample the parameter space efficiently. So there is, of course, we have to continue to do this. I'm not saying that it's not useful. It's very useful, precisely because it's complex. But there is a potential in a gradient method like the adjoint method to assess first-order estimates of these main landscape evolution in gradients, and that we can then couple with more complex forward models once we have resolved the first order value of this coefficient. Thank you.
Thanks, Carole. We have time for maybe a few questions.
Irene?
Yeah, thank you for the interesting talk. Yeah, it's more a question about understanding, if I understand correctly what you did. So on the last map you showed, the comparison of the model output and the data, the incision rates. You
Which
showed
one?
that...
This one?
No, and before the first conclusions. So there was, I think it was like the highest site where the model did not fit the data, right?
Yeah.
And
here. Okay.
Yes, I think the blue one on the right.
Yeah.
It's the highest site, right? Or
Not the highest. The highest one is here, but it's mainly it's so recent that we couldn't resolve it with the model.
Okay, that was okay. Then maybe because actually in your first part, I was wondering how you account for the difference in lithology, because the measurements you do in the glacier proximal part. I mean, that's sediment, right? You cannot. How do you compare that with the bedrock data?
That's why it doesn't work. That's why it doesn't work in the upper part of the massif, is that we don't, for the moment, we don't take into account lithological variations. And you're right that here in the upper part of the massif, if you look at the first landscape that I've shown you, it's very soft sediments, moraine and so on. So we cannot reproduce this. And in this area here, the incision rate that we measure is much higher than what we predict. And this must be also an effect of the lithology. And probably because this valley was in fact covered by fluvio-glacial sediments that have been washed out during the deglaciation. But this was not taken into account in the model. So the erodibility here is much too low to account for this process. But we didn't implement variable erodibilities because it was one other parameter to tune.
Yeah, thank you very much for a very, very interesting talk. I was wondering about the first part that you show with the data set, actually, and the Tinée and Vesubie River and all the river that you sample to derive the incisional rate. So if I understood correctly, what you're doing is that you're sampling basically the nick point of the cliff, so the upper part, the most upper part.
Everything from the river.
So you're doing a profile?
Yes, vertical profile.
A vertical profile, and also from this you derive exposure range. But so I was wondering, did you check the age, the onset of the incision?
Sometimes, yes.
And compared to some glacial retreat age that you would have on the upper part, to see whether there would be a correlation, I would say, because it's very interesting that you have most data are LGM, let's say, except one river that seems to have recorded an older incisional history. So yeah, I was wondering, could you see a correlation between the different, retreat and advance of the glacier if you have some data of moraine on the upper part and the onset of this incision on some of the river?
It's difficult to be sure that you sample the cliff all the way up to the onset of incision. This is what we tried to do, because the cliff is easy to identify on the field, and above it you have a more gentle hill slope. So it's possible that we try to get sure as much as possible that we have sampled everything from the riverbed to the top of the cliff, but sometimes it's not possible because the things are too degraded and you can sample everything. So yes, there is a correlation, especially here. You see that there are many, many points that are younger than 20,000 years, which doesn't mean that we didn't try to take samples above, but which means that simply above this, it was the top of the cliff, and there is no more evidence of very strong river incision and downcutting. So there must have been some changes in the climatic. It doesn't mean that there was no river at that time. It means that the rate of incision has strongly changed. And yeah, that's what we can do. And yeah, that's what we can do. And what we can say from these examples is that the onset of very fast river incision is around 20,000 years.
Okay. Thank you very much, Carole, again.